We can also discuss relative solubility. So you could take two insoluble compounds and compare how soluble they are and indicate that one is more soluble than the other. So this is a precautionary tale of why you can't use KSP directly for a lot of things. So KSP, we're going to compare magnesium hydroxide versus iron carbonate. Magnesium hydroxide has a KSP of 2.06 times 10 to the minus 13. Iron carbonate has a KSP of 3.07 times 10 to the minus 11th. So just looking at the KSP, equilibrium constants, the iron carbonate has a bigger equilibrium constant. Now that just tells us the solubility product at 25 degrees Celsius. That's it. We have to compare the molar solubilities because if we're saying which is more soluble, we're saying like which has more in the solution. And molar solubility is the thing that tells you that. It's the concentration in solution of 1 mole of the compound. So calculating molar solubility, you should go ahead and pause here if you want to try to do this calculation. When you do the calculation, you should get for magnesium hydroxide, the molar solubility is 3.72 times 10 to the minus 5th. But for iron carbonate, the molar solubility is 5.54 times 10 to the minus 6th. So the magnesium hydroxide is more soluble. Even though the KSP value doesn't directly reflect that, when you calculate the molar solubility, there is more of the magnesium hydroxide in solution than there was of the iron carbonate. Now, the main reason we can't use KSP to compare here is because the stoichiometry doesn't match, right? I would split magnesium hydroxide up into 1 magnesium and 2 hydroxides. And for iron carbonate, I would just get 1 iron and 1 carbonate. So I get more ions in solution from the magnesium hydroxide, and that affects the solubility. And you see it come out in the molar solubility calculation. Now, if the stoichiometry matches, you can just compare the KSP. So if it was iron carbonate and then something else that just had a 1-to-1 ratio, so something, I guess, like barium carbonate is also insoluble. Iron carbonate versus barium carbonate, you could compare the KSP, but iron carbonate versus magnesium hydroxide, you cannot. All right, so this is how you compare solubility. Let's talk about solubility in something other than pure water. So the question that I want you to ponder and that we're going to answer is, would you expect silver chloride to be more soluble in pure water or in 0.1 molar sodium chloride? Now, intuitively, you can kind of think about this. Solubility of silver chloride. How do we deal with solubility? Write the equilibrium. Look at the equilibrium, and is there anything that would affect the equilibrium in one of these? The answer is absolutely yes. So I would expect this to be more soluble in the pure water because in the sodium chloride solution, I already have chloride ions. So when I'm doing my equilibrium table, my initial row under chloride is not 0 if I'm in the sodium chloride solution. We're going to do this calculation to show you with the numbers that this is the case, but this is the common ion effect. So remember, this is just, it's Le Chatelier's principle, and it's the presence of the Cl minus that causes the equilibrium to shift left relative to the equilibrium in pure water. So in the sodium chloride solution, less silver dissolves. Now this is sort of, right, that kind of, for Le Chatelier, we talked about being at equilibrium, doing something, seeing what happened. This is kind of like putting in the perturbation first and then letting the reaction try to go to equilibrium. It won't be able to go to the same spot because it has that addition of one of the products that's already in the solution. So in pure water, the solubility of silver chloride was 1.33 times 10 to the minus fifth. Let's calculate the solubility in 0.1 molar sodium chloride. So calculate the solubility of something. It's an equilibrium problem. We need a Rice table. Our reaction is the silver chloride dissolving, and my initial conditions include chloride. So my solution that I'm trying to dissolve silver chloride in, it has water and 0.1 molar sodium chloride. Sodium chloride is soluble completely. So that means it's 0.1 molar sodium and 0.1 molar chloride. So the 0.1 molar chloride is what goes in my initial row under Cl minus. Now I don't have any silver in solution, so my reaction is still going to go to the right. I'll have X and 0.1 plus X in my equilibrium row. Set that equal to the equilibrium constant, which is my KSP. And I'm not even going to make you solve this all the way out. Assume that X is small. And for solubility problems, you don't need to test the result. You can, these equilibrium constants are tiny. You can always assume that X is small and that using X is small will work. You don't need to test it to show. So that leaves me with 0.1 times X equals 1.77 times 10 to the minus 10th. So my molar solubility in 0.1 sodium chloride is 1.77 times 10 to the minus 9th molar. So having 0.1 molar sodium chloride took my solubility from 10 to the minus 5 to 10 to the minus 9. That's 4 tens apart. So that's 10 to the fourth apart in magnitude of the concentration that's possible with and without a common ion. All right, what about pH? So let's look at the pH and what is going on in these solutions. So let's say that we have magnesium hydroxide going into solution, right? It's in equilibrium because it's an insoluble salt. If the solution is basic, I would expect this to be less soluble. Now, the reason why is because if the solution is basic, we have a high concentration of OH minus, which is a common ion for magnesium hydroxide. So there is hydroxide already in solution. So this is going to block the magnesium hydroxide from dissolving, or right in Le Chatelier terms, the reaction would shift left. So the magnesium hydroxide would be less soluble in a basic solution. Now, magnesium hydroxide in an acidic solution, my base reaction is the same. It's still the magnesium hydroxide in equilibrium with the cation and anion. Now, if my solution is acidic, that means I have H plus around. Well, we know from many practice problems at this point that acids and bases react with each other. So if there's H plus in solution, that's going to react with the OH minus and produce water, which is a weak electrolyte. It doesn't split back up. So that OH minus that reacts with the H plus is removed from the reaction. So having acid around removes a product from this equilibrium, and it makes the equilibrium shift to the right. Right, I'm using up product, so the reaction's going to go to the right to make more product. If there's enough acid, it's going to keep removing the OH minus. You could get the magnesium hydroxide to fully dissolve if the solution is acidic enough. And so this is why in some of the solubility tables, you'll see things marked as being soluble in an acidic solution, but not in a neutral solution. And I mean, I don't think I've ever seen any listed as being soluble in a basic solution, but there are some that would work. Um, so, right, this is why, because an acidic solution removes product, which, thanks to our friend Le Chatelier, lets us know that the reaction is going to shift to the right to accommodate that change.